Okay, and then the last little bit I want to talk about is stratospheric ozone. Just a reminder, you've seen that graph of the layers of the atmosphere a number of times. So the stratospheric ozone layer is about 45 kilometers above Earth, extending upwards to 60 kilometers. And it's important because in the stratosphere where you have this layer of ozone, or the ozone layer, that ozone layer has this unique ability to absorb ultraviolet radiation, which in turn protects life on Earth, particularly multicellular life, which is particularly sensitive to DNA damage from UV radiation. The creation, or I should say the formation of the stratospheric ozone layer in Earth's history was sort of a culminating moment evolutionarily, because that's really when we saw a major explosion in the complexity of life on Earth. So here's how ozone forms and breaks down. It's, one of those reversible reactions you learn about in chemistry, so it can drive forward and backwards. So we're going to have UVC radiation that comes from the sun, and that radiation can actually break the bonds that hold together oxygen gas. So you take an oxygen gas, or O2, and you end up with two free oxygen atoms. And of course, if you have free oxygen atoms, then they might combine with O2 to form O3, and now you have ozone. But ozone itself can also be broken down back into O2 and free oxygen atoms, and it will do that when it absorbs UVB, ultraviolet light, and UVC. So the presence of UVC and UVB ultralight can drive that reaction back the other way. And, just connection, and if you remember, but you might have learned about Chatelier's principle in chemistry, that whole thing that reactions reach an equilibrium unless a condition upsets or disrupts that equilibrium, and then it will drive the reaction in the direction that best offsets and returns it to equilibrium. And that's kind of what happens here. But what's particularly unique about this is that ozone absorbs UVB light, and that's the only molecule in the atmosphere that absorbs UVB, and UVB is a carcinogen. It causes DNA damage in living things. So we also have done our fair share of contributing to the breakdown of the ozone layer. So some chemicals that we have made, particularly chlorine, are capable of breaking down ozone. And the biggest source of chlorine in the stratosphere is from CFCs, or chlorofluorocarbons. These were used in refrigeration and air conditioning up until not that long ago, but also in aerosol cans and other blowing agents that inject air into foam products. Most of those have been banned for significantly longer than the refrigerants, which have now shifted away from CFC, so you don't get CFC refrigerators and air conditioners anymore. And that's having a difference. It's been, I think, maybe 30 years or something, and we're starting to see a repair in that ozone layer where there once had been a significant amount of damage to that ozone layer from CFCs. Also, I think it's like rocket fuel and flame retardants, they also can act as ozone destroyers if those pop up anywhere. So when CFCs are released into the troposphere where we are, they float upwards and make their way into the stratosphere, and the ultraviolet radiation that's present has enough energy to actually break the bond that connects chlorine within the CFC molecule, and now you have a free chlorine, and that free chlorine is really good at reacting with ozone molecules to break them up. So essentially this is what you see. So chlorine is going to break the ozone's bonds, and it will pull off one atom of oxygen and form a chlorine monoxide molecule and an oxygen gas, or O2. And then the free oxygen atom is going to pull the oxygen atom from the chlorine monoxide, which liberates the chlorine, and that means the chlorine can now catalyze the breakdown of another ozone molecule. So literally a single chlorine can catalyze the breakdown of as many as 100,000 ozone molecules before it leaves the stratosphere. The College Board loves this concept. So, I'd say there is definitely a chance that something like this could show up on the exam, and you would definitely want to be able to talk about these chemical reactions and describe how chlorine has such an impact on the ozone layer. Global ozone concentrations have decreased by more than 10%. The depletions were worse at the poles. And of course, reductions in the stratospheric ozone increased the amount of UVB radiation that reached Earth's surface, and that could, potentially have impacts on living things and humans. So just refreshing our memory, it was in 1986 when nations first started meeting about how to reduce the ozone destruction, and it was in 1987 that the Montreal Protocol on Substances that Deplete the Ozone Layer was first signed, and the idea there was to resolving to reduce the CFC production by 50% by the year 2000. It was a big deal, and it ended up being 180 countries signing on. And we ended up addressing over 96 ozone depleting compounds, and therefore the concentration of chlorine in the stratosphere has stabilized at about 5 parts per billion, and they expect it to be as low as 1 part per billion by 2100. It takes a long time for us to see the reduction despite all the constraints on products that contained ozone destroying chemicals, because the chlorine stays around so long in the stratosphere. So it takes a long time, but we're starting to see the effects now. So that's the good news. There is actually good news on this front. All right, and that's it for me on these two topics.